Okay, a question about pressure. So we've got this tank here. We've been given the dimensions and we're told the pressure at the bottom of the tank is 12 kilopascals. State the equation relating pressure, force and area. Okay, you need to know this equation. It needs to be at the tip of your fingers. So if you don't know it, commit it to memory forever, right now. Pressure is force over area. Or pressure is the force per unit area. Okay? Right. Calculate the weight of water in the tank. 4 marks. Right, no problem. So this tank's full of water apparently, and it wants the weight of the water, and we know the pressure. Right, weight means, well, the unit of weight is newtons, okay? Don't confuse mass and weight. So weight is a force. So it's the force exerted by this mass of water on the bottom of the tank, okay? So calculate the weight of the water in the tank. So in other words, we have to find force, okay? We have to rearrange this equation to make force the subject. Well, that's easy enough. We multiply both sides by area and we get force. Therefore, force is pressure times area. Okay? Well, we've been told the pressure. What about the area? Well, we just need to work out the area of the bottom of the tank. Okay? So, the area is, that's easy, it's 2.4 times 1.5. 2.4 times 1.5. Okay? So therefore, the force is pressure. Now, it's 12 kilopascals. And 1 pascal is 1 Newton per meter squared. Okay? You have to get your units right, and we always work in newtons and meters squared. So if we've been given 12 kilopascals, so 12 kilopascals is 12,000 newtons per meter squared, okay? Or 12,000 pascals. So like I say, we have to work in newtons and meters squared, so we need to remember to use 12,000 and not 12, okay? So therefore, the force is pressure times area, 12,000 newtons per meter squared times the area, which is that, 2.4 times 1.5. Stick it in your calculator and you get 43200 newtons. And that is the weight exerted by the water. That is the weight of the water. Okay, good. Nice, easy 4 marks. Right, this bit now. Which diagram shows the direction of forces from the water on the tank? Okay, that's important. Not the tank on the water, it's the forces that the water is exerting on the tank. So, it can't be D, because it's talking about the forces the water exerts on the tank. And these forces are all directed towards the water. So that looks like, might be the forces exerted by the tank on the water. Okay? This one is a mixture of both. You've got one force acting on the tank, but you've got these two forces acting sort of on the water. What about this one? Well, pressure acts in all directions. So you have all these 3 arrows all pointing down, all the force going down. You do need an arrow going to the side as well, because the water in the tank will exert a force on the sides as well as the bottom. Okay? So therefore, it's got to be this one. It's got to be B. And that's correct. The water is exerting a force on the base of the tank and on both of the sides. Okay, its pressure acts in all directions. So it's B. Okay, that is correct. Good. Right, now I need to clean the board. Okay, let's go. So, we have these three containers here. This one has water in it, this one has mineral oil, this one has water. We've been given this data and we have to explain which container has the highest pressure at the bottom and which has the lowest. Okay, now it says explain, it didn't say calculate, so you can get the marks just by explaining in this question. So let's start with an explanation, and then you can also get the marks by doing the calculation, and we'll do that too. We'll do it both ways. Okay, so explain which has the highest pressure and which has the lowest. Right. The pressure at the bottom of these containers here doesn't depend on the width of the container, okay? The pressure depends on the depth of the liquid and the density of the liquid, okay? So, let's compare A and C to start with. They both contain the same liquid. It's both water, okay? And we know that A is twice the depth of C, 50 centimeters to 25, okay? So it doesn't matter about the width here, the container. The depth of this is twice the depth of that, and they have the same density. Therefore, the pressure at the bottom of A would be twice the pressure of C, okay? So let's write that down. A has same density and twice the depth as C. Therefore, A has twice or 2 times the pressure of C. Okay? Good. Right, let's compare A and B now. The depth is the same. Okay, it's 50 centimeters. So the difference in pressure between A and B will be dependent purely on the density of the liquid. Well, let's look at the densities. It's 1 to 0.91. A has a slightly higher density than B. Okay? So A has slightly higher density than B. So therefore, oh, and the same height, same depth of material. So we're using, the word depth, Therefore, A has higher, slightly higher, pressure than B. Okay? So we've done it. A has higher pressure than both of them. So A has the highest pressure. A has, because of the 1 to 0.91, it has a slightly higher pressure than B. So B is next. And then A has twice the pressure of C, so C has the lowest pressure. Okay? So that is how you would explain it. Okay, and that would get you the 3 marks. Now, let's calculate it, okay? So, we are aiming for pressure. We want to know, we've been given the area, the liquid, the density, the depth. We want to know what the pressure is. So let's introduce a column for that, okay? Now, pressure at the bottom of these containers is the force or the weight of the material divided by the area at the bottom, okay? We've been given the area. So, pressure is the force of the liquid. So we need to calculate the weight, because weight is, as units of newtons, weight is a force, okay? Force over area. Right, so we know the area here, we don't know the force. So we need a column for the force. Okay. How do we get the force? Force is, how do I do this? Force is the weight, which is the mass times gravitational field strength. So force is mg, where m is the mass of the liquid, okay? We don't know the mass, but we do know the density, okay? So we also have to use that density is mass over volume, right? So, therefore, mass is density times volume. We know the density, and we know the volume because it's depth times area. So, right, we know the mass. The force is that which is known, and G we know, right? So we can work out the pressure because we know the area as well. Okay, so let's have a column for the volume of the liquid. There, okay, so we need volume of liquid. Okay, and let's have a column for the mass of the liquid. Right. So if we work out the volume and the mass for liquid through these equations, we can get the pressure. Okay. Okay, so therefore the force is m times g, d times v times g. So therefore the pressure is dvg over A. So the pressure is the density of the liquid times the volume times gravitational field strength divided by the area. Right. So let's work out the volume. Volume of the liquid. Right. Volume is the area times the depth. So this is 16 times 50, which is 800. Be careful of units. These are both, that's centimetres and centimetres squared, so it's centimetres cubed. Okay, this one is 32 times 50, which is, well, it's going to be twice that, so 1600 cm cubed. This one is 12 times 25, which is 300 cm cubed. Okay, right, so we've got the volume. Now the mass is the density times the volume. Okay, here it's going to be the mass. So density times volume. So this is density times volume. So that's just looking at the units, cm cubed and grams per cm cubed. So we multiply grams per cm cubed by cm cubed, we end up with grams, not kilograms. Okay, just looking at the units. So one mass is density times volume. So D times V, mass M equals density times volume. D times V, 1 times 800, which is 800 grams. Okay? Here, density times volume, 0.91 times 1600, which is 1456 grams. Here, density times volume, 1 times 300 is 300 grams. Okay, so we've got the mass. Right, so we can work out the pressure finally. So pressure is, well, we could have worked it out all in one here, but I've broken it down into mass and volume. So pressure is also mass, density times volume, mg over A. So that's what we're going to use here, because we've got mass. G, we're told to use, or are we told? Let's just take G as 10. No, we're not told. Doesn't really matter whether we choose 9.8 or 10. Let's just take G, acceleration due to gravity or gravitational field strength, as 10 newtons per kilogram. Okay? Right, so we've got the mass, we've got G, the area, we've got the area, we can work out the pressure, finally. So, mg over A, mass. Now, let's get the units right. G is newtons per kilogram, so we need to have the mass in kilograms, okay? So that's 0.8 kilograms, that is 1.456 kilograms, and that is 0.3 kilograms. So, pressure, mg over A. I'm going to use mg over A. Right, mass is 0.8 times 10 mg over the area. Right, we've got to get the area in meters, okay? We work in newtons, kilograms and meters. we've been given centimetres squared, we need to convert that into metres squared. This is how you do it. Write this down if you need to work it out in the exam. Okay, you say that 1 centimetre is 0.01 metres, which you know, right? Therefore, 1 centimetre squared is 0.01 metres squared. Okay? And 0.01 squared is 1, 2, so it's going to be 4 decimal places. 0.0001 metres squared. 1, 2, 3, 4. That's correct. Okay? So 1 cm squared is 0.0001 metres squared. Okay? So that's how you convert it. So, therefore, 16 centimetres squared is, move the decimal point 4 positions, 0.0016 metres squared. Okay? So it was there, the decimal point, 1, 2, 3, 4. Okay? So 32 cm squared is therefore 0.0032 metres squared, and 12 centimetres squared is 0.0012 metres squared. Okay? So remember that technique. That's how you convert from cm squared to metres squared. Right, so pressure is mg over A, mg over the area in metres squared. You've got to get the units right. And that is 0.0016 metres squared. Stick that in your calculator and you get 5,000 units of pressure. You can use pascals, so 1 pascal is 1 Newton per metre squared. Both are correct. Let's use newtons per metre squared, so 5,000 newtons per metre squared. Okay? Right, for B. Pressure, mg over A. Mass is 1.456 kilograms times g, which we've taken as 10, divided by the area in metres squared is 0.0032. Stick it in the calculator and you get 4550 newtons per metre squared. Good. For C, mg over A, mass is 0.3 times g, which is 10, over area is 0.0012 metres squared, and that turns out to be 2,500 newtons per metre squared. And we've done it. Okay? We've worked out the pressure of A, B and C. And they are, for A, it's 5,000 pascals or newtons per metre squared. For B, it's 4,550. And for C, it's 2,500. So, from our calculations, it's A has the highest, then B, and then C, which agrees with our earlier descriptive analysis. Okay? Great. Let's see why that's the case. So we said we're going to check. A has the same density and twice the depth of C, therefore A has twice the pressure of C. Does A, now we've calculated it, have twice the pressure of C? 5,000, 2,500. Yes, it's twice the pressure. We also claim that A has a slightly higher density than B and the same depth. Therefore, it has slightly higher pressure than B. Is that true? A has slightly higher pressure than B. Yes! We have smashed it. Okay, so it's only a 3-mark question. Under exam conditions, you saw how long the calculation took. I would strongly recommend, under exam conditions, to do it like that, much faster. Okay, all based on the fact that pressure depends on depth and density. Okay, remember that, and you can analyze the question using that, like so, like we did. Okay, so under exam conditions, you can get the 3 marks that way because it's much quicker. However, if you want to do the calculation, you've got time, nothing wrong with that. Okay? So, yeah, that's it, okay? Good. I just want to say a couple of things to finish off. The pressure in these containers depends on the depth of the liquid and the density of the liquid. It doesn't depend on the width of the container, okay? And that's interesting, right? In other words, it doesn't depend on the area here. If you had another container here, right, which was like A, right, but had, okay, so another container containing water at the same depth as A, okay? So same liquid, so same density, same depth, okay? The pressure in both of these is the same. Okay, that's very important. Remember that, and you can answer the question just using this analysis. So if you change the width or the area of the base of the container, it doesn't affect pressure, right? Only the height of the liquid and the density of the liquid do. And if you're interested, I will talk about this a bit more. You can switch off at this point if you want. This is just extra interesting knowledge, if you like. So it doesn't depend on area, and we saw that borne out in the calculations, right? The area of the base was used in these calculations. We used it to calculate the volume here, okay, it's there. So it's embedded in this number here, the volume, and it's therefore embedded in the mass because we multiplied by the density to get the mass, okay? So the area is in 0.8 kilograms, so it's embedded, it's in this number here, it's on the top. And then we divided by the area here, okay? So in fact, we had area on the top and area on the bottom, and they cancelled, right? It was kind of hidden in the calculations, but that's what happened. And so from a mathematical perspective, we saw how pressure doesn't depend on area. Clever, right? They cancel, one on the top, one on the bottom. Okay, good. Right. So that's definitely more than enough. Just to summarise, under exam conditions, I would answer the question like this. If you've got time, you can calculate it, no problem. Good, I think that's everything. We'll definitely leave it there.